Okay, so let's think about these two different heat transfer processes in the context of our saucepan example. So firstly, imagine we only have conduction in our system. So we're going to introduce this saucepan onto the hot plate, and we're going to immediately heat the bottom of the saucepan, heat the water at the bottom, and those molecules are going to jiggle around and transfer that heat up to the layer above, and so on and so forth. We're gradually going to heat through that water column. This is what happens. You just develop this linear gradient of temperature through the water column from the bottom temperature T, which is warmer, to the cooler surface temperature T minus delta T. So that's what you get if you have a purely conductive scenario. Now let's allow the fluid to flow. So let's add in our convection. So as we know, if we heat a small patch of fluid, so for example, this small patch here, this fluid's going to be warmer than the surroundings, and it's going to tend to rise. So we're going to get this rising plume up here. And similarly, if we cool a small patch of fluid near the surface, that's going to sink. And so we expect the result of those two things to be a circulation in the water, an overturning circulation that is efficient at transferring heat. So let's look what happens in this scenario. Okay, so you can see you get the formation of these plumes initially, which gradually settle out into these stable overturning structures, just like we've drawn in the schematic. And you can see, in contrast to the diffusive or the conductive case, you have a very well mixed interior of the fluid because the convective transfer is quite efficient. So you have a warm bottom layer, a well mixed interior, and then a cooler surface layer. And so you end up with an average temperature profile through the fluid that looks like this.